So welcome back. In this particular module, we will discuss about the overview of p-n junction diode. So what is a diode? Diode is a semiconductor device that allows the current to flow through it in one direction only, but restricts the current flow in the opposite direction. So the simplest solid state component is a p-n junction diode. Okay. So this is the symbol, schematic symbol of your p-n junction diode. This is the P side and this is the N side. Okay. N side is called the cathode and P side is called the anode. So how will you form a p-n junction diode? You have an intrinsic semiconductor, you dope it with the pentavalent impurities, you will get the n-type semiconductor. You have the intrinsic silicon, you dope it with trivalent impurities, you will get p-type semiconductor. Now you have separately formed n and p-type semiconductors. Okay. Now by using the deposition techniques, various deposition techniques in fabrication process, we can make the p-n junction diode. Okay. Now we will see what is the mechanism of this p-n junction diode. Okay. Now in inside what we have? In inside we have the excess of electrons. So these minus signs that you are observing here, these are electrons, and these electrons are majority carriers in n side. And in p side what we have excess of holes. So these plus signs, they indicate the holes. Okay. Now when a p-type semiconductor and n-type semiconductor, you are joining them, what will happen? The electrons from the n side, they will diffuse from n side to p side. Now I used a term here called diffuse. Diffuse comes from the word diffusion. Diffusion is a property through which the charge carriers, they will move from high concentration gradient to the low concentration gradient. So in n side we have electrons, they are present in high concentration, so they will move towards the hole side. In hole side also we have electrons present, but they are minority charge carriers there. Similarly in from p side also holes will diffuse from p side to n side. Okay. Now when this electron, when it reaches to the p side, it recombines with a hole. Okay. When this electron recombines with a hole, the hole will get vanished and the electron, it will no longer remain free or mobile. So all these electrons that you are observing here, these are free electrons. Okay. So when this electron, it reaches to the p side and it recombines with the hole, it no longer remains free or mobile. Hole gets vanished and electron, it remains no longer mobile. So what we observe, at a time two charge carriers are getting vanished in this recombination process. Okay. So, and when this electron, it leaves from this n side to p side, it leaves behind a positively charged donor ion. So for each and every electron that is leaving from n side to p side, a positively charged donor ion will be left behind. Similarly, for each and every hole that is leaving from p side to n side, a negatively charged acceptor ion will be left behind. So as these electrons, they diffuse from these n side to p side and they recombine with the hole, and as the charge carriers, they get vanished, more and more recombination as it keeps on happening, what will happen? At the junction we will have this donor ion and the acceptor ion. Okay. So in the n side we will have more concentration of the donor ion, and in the p side we will have the more concentration of the acceptor ion. Okay. Now these donor and these acceptor ions, they are not free charge carriers. the electrons in the inside and the holes in the p side, they are free charge carriers, but these donor and these acceptor ions are not at all free charge carriers. They are immobile charge carriers. So, and they don't conduct any electricity. Okay, so the region that consists of these donor and the acceptor ions, it is basically an insulating region. Okay, within this conductive and doped semiconducting region, this is a conductive region, this is a conductive region, but this is an insulating region which consists of my donor ion and the acceptor ion. So this region is called the depletion region or the space charge region. So that means what we can see, a barrier is getting created at the PN junction. So once this barrier is getting created, electrons from this N side, they can no longer diffuse from N side to P side. If they want to diffuse, they need to cross this barrier. So this, in this barrier we have one side, these are positively charged donors, these are negatively charged acceptor. So a potential is getting developed. Okay, so that potential is called built-in potential. Okay, now if I want, this is an unbiased PN junction, we didn't apply any external battery voltage here. If I want these electrons to diffuse from N side to P side, I need to apply a potential. Okay, now this situation I explained in case of the unbiased PN junction. Okay, in unbiased PN junction, what is happening, this barrier is getting formed, and when these electrons, I want them to cross from N to P, I need to apply some voltage. Okay, because a barrier is already created. Okay, same for the holes. If they want to diffuse from P side to N side, then we need to apply a barrier potential. Okay, now let's see. Now we are applying an external battery voltage, and that means we are forward biasing the PN junction. So why we are calling it forward biasing? Because P side is connected to the positive terminal of the battery and N side is connected to the negative terminal of the battery. So in this depletion region, what is happening? We have positively charged donors here, we have negatively charged acceptors here. So an electric field will get developed. And what is the direction of the electric field? Electric field is a force on a unit positive charge. So in this barrier, the electric field is from right to left. Okay, that means from positive to negative. Okay, but due to this external battery, what is the electric field? From positive to negative. That means here it is right to left and here it is left to right. So due to these opposite direction of the electric field, the effective electric field in this depletion region, it reduces. Okay, now due to the forward biasing, electrons and holes from the N side and P side, they move toward the junction. Okay, so as we keep on increasing these battery voltage, the effective depletion region width reduces. So as the depletion region width reduces, it is easier, it becomes easier for the electrons to cross the barrier and reach to P side, and it becomes easier for the holes as well to cross the barrier and reach to the N side. Okay, and when this applied voltage, it becomes higher than the barrier potential of this PN junction, the resistance offered by this depletion region becomes negligible. And what happens now? It becomes completely easier for the electrons to cross this barrier, and it becomes completely easier for the holes to cross this barrier, and your PN junction diode starts conducting. Okay, the voltage at which your PN junction diode starts conducting is called the cut-in voltage or knee voltage. Okay, if we plot this situation with the graph, this is my battery voltage VD, and this is the current that is getting across the diode. So first, when these external potential is low, battery voltage is low, we are not getting any current, almost zero current. But these when this cut-in voltage arrives, okay, that means what we have seen, when this voltage is higher than this barrier potential, the resistance offered by this region becomes negligible, no? So that time what happens, your current starts flowing, because the charge carriers now they are capable of moving to the opposite side, and you are getting a large amount of current is exponentially increasing. So this VT is my cut-in voltage, which is 0.6 volt for silicon and 0.2 volt for germanium. This is my forward bias region. Okay, now actually when we will draw this depletion region in the forward bias situation, we should keep the width low, because the electric field are opposite direction, no? In this region the electric field is right to left, and for this battery it is left to right. So due to these opposing electric field, the effective electric field in this region reduces and the depletion region width reduces. If we keep on increasing this voltage, this width will get reduced. So in forward biased PN junction, we must keep this width of the depletion region less. Now coming to the reverse bias. What happens in the reverse bias PN junction? Now this P side is connected to the negative terminal of the battery and N side is connected to the positive terminal of the battery, because it is reverse biased. Now let's see what is the direction of the electric field. In this region, in the depletion region, electric field direction will remain as it is, right to left, and due to this external potential, electric field direction is now positive to negative, right to left. So now both of these electric field directions are same, right to left, and due to these same electric field direction, the effective electric field, what will happen, this effective electric field in this region, what will happen to this effective electric field? Both are in the same direction, no? Both are in the same direction. So these effective, previously what happened in the forward bias region, since it was in the opposite direction, so effective electric field was getting reduced. Now here, since both these electric field are in the same direction, so effective electric field in this region will increase and the depletion region width also will get increased. As you keep on increasing this battery voltage or reverse bias voltage, your depletion region width will get wider and wider, and in this case it will be completely impossible for the electrons to cross this depletion region and reach to the other side, and it will be completely difficult for these holes as well to cross this wider depletion region and reach to the opposite side. Okay, however, we won't get any current flow through this circuit now due to the majority charge carriers, but some current we will get due to the minority charge carriers. We know in the inside we have holes present as the minority charge carriers. In the P side we have electrons present as the minority charge carriers. So those minority charge carriers, they will contribute very less amount of current, and that current is known as the minority charge carrier current or reverse saturation current. Okay, and this current is in the order of nanoampere. Okay, 10 to the power minus 9 ampere or 1 nanoampere in case of the silicon, and it is in the range of microampere or 10 to the power minus 6 ampere in the case of germanium. Okay, now this situation was happening when my diode was operating in the forward bias region. Now we are discussing reverse bias. No, so in reverse bias, as we keep on increasing the reverse bias voltage, your current is slowly increasing, but once a certain point, a certain threshold, which is called the breakdown region, what happens, the current sharply increases, and that means if you apply more voltage, more reverse bias voltage than this breakdown voltage, your device may get damaged. Okay, now what is the diode equation. The diode equation is expressed as I equals to I naught e to the power qv by eta kt minus 1. This I is the current flowing through the diode. I naught is the reverse saturation current. Q is the charge of an electron. Capital V is the voltage applied across the diode. Eta is the ideality factor. K is the Boltzmann constant, and the value is 1.38 into 10 to the power minus 23 joule per Kelvin. And capital T is the absolute temperature. And this eta, it tells you how it is the nearness with which the considered diode behaves with respect to the ideal diode. Okay. Now, in the forward bias condition, what happens? A large amount of current, we have seen it flows through the diode, right? So, in that case, this term, the first term, it becomes large, much large than this one. So, we can neglect this one term. So, in the forward bias situation, the current I becomes I naught e to the power qv by eta kt. And what happens in the reverse bias condition? In the reverse bias condition, this capital V, it becomes negative. It becomes very large and negative. Okay. So what happens? This qv by eta kt term, this becomes, it is much less than 0. Right. So this entire exponential term, it is now tends to 0. Okay. It is now tends to 0. Okay. So what we can write? I equals to minus I naught during the reverse bias. Okay. So what is the temperature dependence of diode characteristics? This reverse saturation current I naught or minority charge carrier current, it gets doubled for every 10 degree centigrade rise in the temperature.